In the Strait of Malacca, a historically calm waterway near the equator, Cyclone Sinyar formed and violently spun toward land. It was only the second time a tropical cyclone had ever been recorded there. High in the Himalayas, glacial lakes burst through their natural dams 6 separate times within a tight 4-month window. In Indonesia, intense flooding submerged coastal provinces, forcing residents to wade through waist-deep water just to reach the local police station. And in North America, thick wildfire smoke completely choked the Los Angeles skyline in January. The 2025 Global Water Monitor report ranks the year as the 3rd hottest ever recorded. The data reveals that the existing models we use to predict the global water cycle are no longer tracking with reality. The events of 2025 exposed a mismatch between the current physics of our planet and the infrastructure we built to manage it. Every modern city, power grid, and dam is built on an engineering concept called a historical baseline. We calculate these baselines using weather patterns recorded over the 20th century. The logic is straightforward. If a river flooded to a specific height once every 100 years, you pour a concrete wall just high enough to hold back that exact volume of water. The Earth's water cycle has shifted away from those 20th century patterns, yet our cities remain locked into those outdated blueprints. This chart from the Global Water Monitor tracks daily maximum precipitation over land. The right side shows a sharp cluster of anomalies. Daily extreme rainfall is increasing by 2.3% every single decade. We see a similar trajectory in extreme heat. This graph tracks hot days above 35 degrees Celsius. Their frequency spiked by 22% compared to the baseline. Zooming in on the final 2025 bar, we see a compounding risk to heavily populated areas. The physical realities of the present water cycle have simply outgrown the blueprints of the past. This global map tracks where infrastructure mismatches turned into major disasters in 2025, revealing how specific systems failed. In Europe, heat waves, now up to 70 times more likely, blanketed the continent. The urban infrastructure there baked under the sustained temperatures. Public health systems were rapidly overwhelmed. With digital thermometers flashing 39 degrees Celsius across European capitals, the mismatch resulted in tens of thousands of heat-related fatalities. In the Caribbean, warmer ocean waters fueled Hurricane Melissa. The storm generated wind speeds and rainfall that coastal defenses could not withstand, destroying entire neighborhoods. Inland, drought severely depleted Lake Kariba in Zambia. As the waterline plummeted down the face of the massive concrete dam, hydropower storage emptied out, causing severe electricity shortages that crippled the regional grid. The final global ledger for the year was devastating. Water-related disasters displaced roughly 8 million people and caused more than $360 billion in economic losses. When the water cycle shifts, the foundational infrastructure of a nation, its dams, grids, and ports, loses its functional utility, essentially neutralizing decades of capital investment. To understand the true financial toll of these broken baselines, we can audit a single microeconomy, Los Angeles County. Extreme heat and prolonged dryness created fire weather conditions 40 times more likely to occur than in the pre-industrial climate. The landscape was primed to ignite. When the January wildfires broke out, the local water supply systems failed under the stress. This structural collapse directly crippled the ability of emergency crews to fight the blaze. The physical damage was extensive. The fires destroyed over 16,000 structures, leveling entire neighborhoods, schools, and commercial buildings down to white ash. An analysis calculated the financial toll of this disaster. The baseline failure is projected to result in $10.1 billion in lost economic output. The collapse rippled through the workforce, projecting 55,000 impacted job years and $4.2 billion in lost labor income. Even a highly resourced Tier 1 global megacity will suffer catastrophic economic paralysis when its environment exceeds its 20th century design limits. The data from 2025 also proves that modernized infrastructure and proactive planning can effectively intercept these massive costs. During massive atmospheric river floods in the Pacific Northwest of the US and Canada, upgraded early warning systems and strict evacuation protocols managed the crisis, drastically reducing the loss of life. In the Himalayas, newly installed monitoring networks on glacial lakes provided advance warnings that completely prevented fatalities during several outburst floods. When capital is deployed effectively, recovery accelerates. In Los Angeles, aggressive debris removal cleared 95% of destroyed parcels in just 7 months, supported by $20.4 billion in partially paid insurance claims. Looking ahead to 2026, the models indicate drought risks for the Mediterranean and Brazil, alongside elevated flood risks across the Sahel and Asia. Rebuilding to 20th century standards in these high-risk zones creates a cycle of recurring loss. Without upgrading the baseline, communities face the prospect of paying for the same structural failures every few decades. Preparedness and resilient design are no longer optional ecological goals. They are the requirements for economic survival in a volatile new world.